Good afternoon, everyone. With warm welcome to introduce our esteemed speaker, Dr. Sanjay Kumar Patel, sir, who has graciously accepted our invitation to be with us today. Dr. Sanjay sir holds PhD from SBNIT Surat and ME from MS University of Baroda, Vadodara. With her distinguished career in education, he has served in various capacities at SUNIT Surat, Department of Chemical Engineering, first as an assistant professor 2006 to 2019, then as an associate professor 2019 to 2023, and since December 2023 as a professor. Dr. Sanjay Sir's research is widely recognized with over 40 plus published research articles in international journals, two patents, and two book chapters also. He has actively contributed to the academic community, presenting his work at more than 20 international and 5 national conferences. In addition to his research, he has impressive track record in thesis and dissertation supervision, having successfully supervised 7 PhD scholars, with one more currently under his guidance, and 10 MTech by research candidates. Dr. Sanjay Sir is an active member of professional bodies like IICHE and Institute of Engineers and has been honored with several prestigious awards for his contribution to the field. We are truly honored to have him with us today and eagerly look forward to his insight. Let's give a warm welcome to Dr. Sanjay Patel sir and hand over this session to him. Thank you, sir.
Uh, Thank you. It's a overwhelming introduction of mine. So without wasting time, I'm sorry that I'm joining late by 10 minutes, first of all. But let me start my presentation to all of you so that we can have enough discussion on this. And particularly, I tried to compile my work towards to meet the requirement of this faculty development program that is focusing on the green chemistry, sustainable agriculture, and food technology. So I'm trying to relate one of the process of chemical engineering that can be very well applied not only for food technology, but also it can be expanded for the green chemistry also. But here, being a chemical engineer, I'll focus one of the process which is known as a crystallization techniques. Okay, and this crystallization techniques then would be supported by the some another energy in form of sound waves, which is known as the ultrasound. So overall, the presentation would be, coupling of this sound wave energy in a crystallization process for the enhancement of some valuable components, or you can say to tailor the product properties. So the title I kept over here is recovery of valuable compounds through various crystallization techniques assisted through ultrasounds, particularly the sound wave energy. So as I said, I'll then have you divide this presentation in three categories. First, I'll have a little bit focus on the crystallization, what exactly the crystallization process and how it is being used, and what are the problems associating with the crystallization problems. And then that problems, how to overcome that particular problems with the various processes or by coupling particularly the sound wave technology, you can say the cavitation technology. Once it will be over, then we'll go for some of the case studies that are targeting particularly the components from the solution with the help of high crystallization assisted with ultrasound, and how ultrasound is, proving the better technology for recovering of this. And little bit I will, try to by this crystallization technology, along with doing some process intensification, like not only the ultrasound, but by making crystallization like that, and how by changing this, how we can improve this crystallization process. That would be the overall presentation of mine. So let us start then particularly with what exactly the crystallization. So I'll say the crystallization is most important separation and purification process for most of the industry. Most of the industry, wherever the final product comes, is in the solid phase. So the problems, or you can say the importance of the crystallization nowadays, particularly for one particular industry, like in pharmaceutical industry, it is been the importance of this process has been drastically increased, because this process has a good control on the product properties. So you can have a better control on the crystallization process, and you can able to control a final product properties. And that facility is being given by this crystallization process, as well as you can club this crystallization process with the other available sources, and easily it can be integrated. So mostly the crystallization process is divided in two parts. The fundamentally, if you require to understand this process, then you should understand what is the nucleation, and then once the nuclei is formed, how the growth of particular nuclei occur to become a crystal, and how you can tailor the operating factors of the crystallization, and that will affect on this nuclei and growth of the crystals. So if I'll look to the sorry, if I look to the problem associated with the conventional crystallization process, then most of the problems I'll categorize only two main majorly problems associated with the crystallization, is that uh, is the handling of the crystal size, uh, and then the shape of particular crystals. So the people required, or the market required, that the product should be having a equal size, correct? The crystals should be a uniform, as well as the crystals should be having the uniform shape also. So there is a requirement of this that there should be uniform crystal size and uniform shape of the crystal that are being produced by the downstream processes. So this, if we can produce a product with the help of conventional technology, then there is still the problems occurs about the size distribution and the shape control of a particular product that is still exists with the crystallization techniques. Uh, so this uh, is due to the fact that in a solution there are the various sites at which the nuclei will grow, or nuclei will create at the different interval or times, and therefore the growth will occur also in a different interval or times. And therefore at the particular time, if you will stop crystallization process, we have a different growth of the crystals, and therefore the different crystal size that we will obtain. That is what the problem, you can say. So you can focus on then how can we control this nuclei creation, correct? If the all location of the solution, if the crystals or nuclei is being created at the equal time, okay, then their growth will occur also in a equal moment of time. And therefore, the ultimate size that will get out of the crystallization process of the product would have also the same size. Correct. So we can at least by controlling the nucleation phenomena, we can able to control the crystal size also, as well as that you in a later case by controlling the growth rate of the crystal, we can have a control on the morphology also. So the most important, the problem associated with these are the crystal size and its distribution as well as the morphology. Correct. So it is going again. Okay. So to control this a particular nuclei or the crystal size, crystal growth, what are the factors that can be controlled? So we should have some idea about this. The driving forces of the crystallization also means how can we uh, tailor the driving forces so that we can have a control on size and shape of a particular product. So basically there are four main methods uh, that are generating this nuclei, or you can say that are responsible to create the crystallization process. Mostly uh, the crystals or nuclei occurs in a supersaturated solution. So it is said that basically four main methods are there to generate the supersaturation. That is, one, we can change the temperature uh, to create the supersaturation. Another is we can remove the solvent. So the term or the technical term, you can say the evaporation of the solvent. Third one is there that by doing the chemical reaction. So we have, we can have these factors, or you can the methods, you can say you can tailor the temperature, you can tailor the concentration of the solvent, as well as you can have a control on the reaction, and by doing reaction you can form some product, and that product should have insoluble in particular reaction media, so it will come out as evolved as a solid phase. So the doing the chemical reaction also we can make a particular product. Okay. So if so the thing is, if sorry, the the crystallization process basically that are depending on the factors like the temperature change or the solution change or by doing the reaction. So overall crystallization process is divided in three categories. Generally, you can change the solvent concentration, so it falls under the evaporation category, or you can say the evaporative crystallization. There is another kind of crystallization which is called as a solution crystallization, in which there are lot of flexibility is with us to change the factors, like we can change the temperature. We can change the temperature to create a particular supersaturation. Then it is known as cooling crystallization. We can change the concentration of the solvent. Okay. And thereby changing that concentration of the solvent, we will give the name for a particular crystallization is known as solvent crystallization. And if you do creation of the supersaturation by the reaction of the reactant, we will give the name that is a reactive crystallization. So the overall crystallization process have divided in three factors, I can say. There is one solute, then solvent, and then supersaturation. So we have to focus on this three words. solute, solvent, and supersaturation, correct? The solute that is in dissolved into the solvent becomes solution, correct? So that means we need to take out the solute from this solution. Then one of technique is this crystallization. There are so many techniques, means other techniques also to remove the solute from the solvent, correct? But here we are using this crystallization techniques. So the overall phenomena of the crystallization is based on the solute solubility in a solvent. So by somehow, if we can reduce the solute solubility in a particular solvent, we can uh, easily remove the undissolved solute in a solution, correct? And that is how that the solute in a solid form can be uh, removed. So these are the technique to generally to change the solubility, means changing the temperature. You can change the solubility of solute of in a solvent, and thereby supersaturation is generated, and the crystallization occurs in this way is known as cooling crystallization. You can add the some non-solvent also in a solution, so that also the solute solubility in that binary solvent is decreases, and thereby the solute comes out as a solid phase in this case. Okay, and third one is reactive crystallization. So the major focus is on to reduce the solute solubility in a solution, and thereby the creating the solutes concentration in the solution above the solubility limit, known as a supersaturation. Okay, so the nuclei are the first form of the embryos of the solid phase, you can say, and it forms due to the clustering and aggregation of the molecules or ions in the solution to a size at which such entities become viable. And rather than dissolving again in a solvent, they will grow. Correct, because the clustering occurs between so many molecules, but some clusters aggregate together and then again dissolve. So that is not a nucleation, but some molecules are become clusters and aggregated and become clusters, and then the diffusion of the molecules occurs on that to become a detectable size. When it will becomes a detectable size, that process is known as a nucleation, and then the mass transfer happens and the crystal growth occurs. So the nuclei is the generally aggregation of molecules to a size at which a particular cluster becomes viable. And then there are primary nucleation, secondary nucleation. In primary nucleation, also homogeneous nucleation, heterogeneous nucleation, that are the types of the crystallize or nucleation occurs. But mostly we would be focusing more on the primary nucleation, because in homogeneous nucleation, the molecules and the that is in form of the crystal which is generated, correct? And in presence of the growth of the crystal, another nuclei are also created. So this has to be controlled very well. So if we can control this nucleation, we can have a control on the size and also the shape of a particular crystal that are obtained after this process. So the main fundamentals that are required to understand this crystallization, or if you want to have a control on this uh, nucleation process, then you should have an understanding of two more definitions. One is known as induction time. Okay, so what exactly the induction time is? It is the time between the creation of the supersaturation and the appearance of the crystals. So the actually, if we will have some solution which is available. If you can look at to this graph, I'll explain through this. This will give you a better idea of this particular induction time. This is solution concentration, correct? And let us see this concentration change over the period of time. Okay. And initial concentration is with us is this of the solution. So as soon as we start some changing the parameters like, the temperature change, let us do the temperature change. Okay. So what will happen exactly as soon as we change the temperature at this concentration, uh, immediately we'll not see some crystals that are generated. There is some process that is occurring at the microseconds, okay, or within a nanoseconds. So initially we'll see that up to here, the point A to point B days, okay. This is a time at which the molecules are just clustering or aggregate to each other. Okay, so aggregation of the molecules between the during this time occurs, but the size is not detectable yet. So up to B days, there is a size, but it is not detectable size. But giving further time, the size will becomes visible, correct? That cluster and aggregation becomes visible. And we can then say that the nuclei of this concentration is starting with this at the point of B, not at the B days. So the time required to achieve this condition of the B is known as induction time. Correct. So the supersaturation, if I can relate this particular induction time, then we know that solubility of a solute is nothing but a saturated concentration, correct? So we will have a saturated concentration, which is denoted here with this C star, correct? This is saturated concentration. And above any concentration above this C star is known as a, supersaturated concentration. So this is saturated concentration. This that means the A point is supersaturated concentration. Okay. So the time required from the creation of the supersaturation, this means initial time of here, if I'll say it's a T0, 2 of this time at the B, this time is known as induction time. And then once the as soon as the size becomes detectable, then there is some lag time is required to for the growth of the crystal. That means at the point C, the mass transfer from the bulk solution will occur on the nuclei size and the crystal growth will start. Therefore, the concentration that is available in this solution will goes decreasing, and it will decrease, and the crystal growth will increase till up to we'll get some equilibrium concentration, or till the saturated concentration, it will achieve a saturated concentration. That means the concentration available for the growth of the crystal is between the C star and the point of the supersaturation created. This is the concentration only which is being utilized for the growth of the crystal. So this is very important of definition that requires to be understood in a crystallization. And if we want to tailor this induction time, okay, if I can able to do this, I can able to tailor that with the help of providing mixing, means by agitating, more speedily agitating, okay, or spontaneous mixing, you can say. Presence of this, some of the impurities already there. Okay, solution viscosity, cooling rate you can increase. So by having the control of this all agitation, impurities, viscosity, degree of supersaturation, and cooling rate, we can have a control over this induction time also. So that is possible. Another definition that also been required to understand here is metastable zone width. So here also I'll have a little bit I'll try to give you a little bit idea on this. That we have here the two curves. Okay, you can say this is solid dashed, not solid line, and there is a dashed line, dotted line on this curve of the concentration versus the temperature. So this solid line is represents the saturated concentration of the solute. So you can say saturated concentration is nothing but it's a solubility limit, correct? So this is a solubility curve, but and then this dotted curve that represents the point of supersaturation at which the nucleation is being started. Okay, so this is the point, or this is the concentration in a supersaturation region at which the clustering becomes a detectable size, means the nuclei is in a nuclei is formed at this concentration level. Okay, so basically the metastable zone width is nothing but the difference between this concentration of the solubility limit to the creation of the nucleation. Okay, so basically it is being controlled by the change in the temperature. Here the example is taken for the cooling crystallization. So if you'll see here on the point B is nothing but it's a solubility limit, correct? At the temperature of T0. So solute is totally in a dissolved form, or solute is at the saturated limit at this point. So this is the concentration initially, okay? And from this, if I need to take out the solute from the, or if I need to separate the solute from the solvent, I need to create some supersaturation concentration at which the nuclei becomes at the detectable size. So the creation of the supersaturation is being done by changing the temperature. Okay, so let us suppose the saturated concentration is at T0, and then supersaturation is created at this limit of temperature at which the first nuclei is happened there in the concentration. Okay, so metastable zone width I will term as the change in the temperature. Okay, so the metastable zone width here would be the T0 minus of T limit for any kind of crystallization, particularly for the cooling crystallization. Okay, so once the nuclei being created at this, concentration level of this point C, then the crystal growth will start to occur, and therefore this is a maximum concentration that is available for the growth of the crystals. Or you can say you will have the change in maximum concentration available for a crystal growth to be occur is nothing but this delta C max. Okay, and this concentration will then be utilized for the growth of the crystal. So if I need to have a proper control on the crystal growth, I should have a control on this delta C max. See, if I'll have a proper mass transfer on the nuclei, means change in the concentration over the period of time, I should have a control on the cooling rate, correct? So if I can able to control this cooling rate, ultimately I'll have a control on the delta C mix, and therefore I will have a control on the growth of the crystal. Okay, so these two definitions, one is the induction time and another is metastable zone width. If we can able to control this two, then we can have a control on the nucleation, or you can say that you will have a control over the crystal size as well as the shape of the crystals. So how to control this, correct? So how to control this particular the induction time and the metastable zone width? So here the use of ultrasound in a crystallization come into the picture, because we have already defined that the problem associated with a simple cooling crystallization or a chemical reaction or a evaporative crystallization, they are not giving a particular uniform size distribution as well as the uniform shape. Okay, because that process do not have a control on the supersaturation and then the induction time and on the metastable zone width. Okay, so these three can be controlled with the help of ultrasound. It is well evidenced, well proved technology. It becomes now and widely used in the crystallization. It is firstly, if so, if it is having a significance, I'll discuss on this little bit, ultrasound, and then we'll uh, go for a case study. Correct. So, please give me a second, okay? So, am I audible? Correct.
Yes, sir.
Okay, so I need to now discuss of ultrasound, what exactly the ultrasound is and how it is affecting the crystallization. Okay, mostly I said already that it is the use of ultrasound. If you will couple with the crystallization process, uh, then tailoring the ultrasound energy or by controlling the ultrasound energy, you do have the control on supersaturation concentration as well as induction time and also on the metastable zone width. Okay, so there is a better control of the all these three terms with the help of this, and therefore we require to study this, or we need to have a better understanding about the ultrasound also. So use of ultrasound in crystallization, it was reported in 1927. Okay, but at that moment of time, the devices of the ultrasound was not uh, giving the accurate results, or the sound that was produced by the device is not was not so uniform. Okay, so that moment of time it was not being evolved, but later when this sound technology being well controlled, so the device that were manufactured, that was giving the uniform size uniform sound wave generation, and then the use of ultrasound in the crystallization becomes prominent. Okay, and in the last decade, we have seen that there is a positive improvement in the utilization of ultrasound in the crystallization. It is already been known as a sonocrystallization process, and mostly this technology is being used there in the pharmaceutical industries, also in the proteins synthesis of proteins and organic compounds and inorganic compounds also. Okay, so what exactly is the if will the sound waves that are being generated by the devices, if they will pass through some liquids. Okay, so if the sound waves which is produced by particular device is passing through the liquid medium, then the medium consists of the a lot of molecules, correct? So the molecules themselves, they will experience some compression and expansion, and this compression and expansion will be happening over the sound waves, which is in a sine wave form. Okay, so the molecules are experiencing the pressure difference of having the positive pressure and the negative pressure, you can say. So when over the period of time, what or over the progression of the sound waves, whenever this the expansion pressure becomes prominent or exceeds the compression pressure, then the small void is being formed there. Okay, and this is, I can say, the one cavity is being formed, and then this cavity is will start to grow. Okay, over the successive expansion cycle of any sound waves. So during the expansion cycle, of the sound waves, the cavity will grow, and during the compression cycle, the cavity will again compress to a smaller radius. Then I can now say it's a bubbles. Then the bubble grow or bubble compress and growth and compress, that will continue till the pressure inside of the bubble is not sustains the bulk pressure of the liquid, then the bubble will collapse. Okay, so when this bubble is collapsing, then it is said that by modeling that enormous form of the energy is being generated. Okay, here it is said like 5,000 degree and 2,000 atmosphere is being generated with the collapse of a particular bubble, and this particular energy is being utilized in a different chemical engineering processes. Okay, so I can say the overall bubble size creation 5:30 lecture challenge. From the creation of the cavity to the collapse of the cavity, oral phenomena, if you can observe, then this phenomena is known as the cavitation phenomena, which is well being represented on here the graphically, from the formation of the cavity, and then the growth of the crystal, growth of the bubble occurs. Okay, over the period of microseconds. Okay, so the bubble is expanded and the compressed and expanded and compressed, and finally the bubble will collapse. Okay, when it collapses, there is a rapid quenching occurs in a liquid media, and enormous energy. You can able to visualize this energy also by uh, having the device of sonoluminescence, and it creates a hotspot there. So this is a phenomena that we would like also to use for crystallization process over here. Okay, so as I already said, that when the collapse of the bubbles occurs, then we will have the enormous form of the energy in form of the temperature is 5,000 Kelvin to the almost 10 to 5 kilopascal. Okay, and also there is an enormous heating and cooling rates, mostly 10 to 10 Kelvin per second. This heating or cooling can be possible in submicron reactors. And when the that particular bubble is collapsed, then the collapse is divided in two categories. It can be happen like symmetric collapse can also be possible, and there is an asymmetric collapse. So when the symmetric collapse occurs, then very fast shock waves are generated around 4,000 meter per seconds, and with the high pressure amplitudes 10 to 6 kilopascals. And when asymmetric collapse of the bubble will occur, then the high speed of the jet of liquid with the highest velocity, okay, more than 100 meter per seconds of the velocities are being generated during this asymmetric collapse. So there are the various ways by which the collapse of the bubbles will help for the different process, which is in utilized for the different chemical processes, like to accelerate the rate of chemical reactions, or to create the new reaction pathways, or even to generate different products from those obtained under conventional process. So which is energy which needs to be utilized for crystallization process. Okay, so how we can say a particular induction time and metastable zone beats are being affected by the use of sound? It is already been proven, some literature study. So to give a proper idea, I had taken one example of this. Means this has already been proven value. Here in the induction time of roxithromycin in anti-solvent crystallization was studied. On x-axis, y-axis, you can see the induction time, on x-axis, the different supersaturated level is taken. Okay, so this was studied, induction time was studied in presence of ultrasound and without the presence of ultrasound. So the upper curve shows the without ultrasound and lower curves So in presence of ultrasounds at 20 kilohertz. So we can see at the different super saturation, we can clearly see there is a drastic reduction in the induction time is being observed. Correct. And particularly, you can target this zone at the low supersaturation level. Low supersaturation level also, we can see the drastic reduction in the induction time. So this is something which cannot be obtained by the conventional cooling crystallization. The conventional cooling crystallization can happen. It means even we can increase the supersaturation level, induction time can be decreased, but that is not a solution. So that is not also cost effective because it requires a lot of time to create this level of the supersaturation. So there is and also there we will not have any uniform concentration, and therefore these the reduction at the low supersaturation level itself, drastic reduction in the induction time, which is being obtained when we will apply ultrasound in a crystallization. So it's a proven one that at low supersaturation it is being generated. Okay. And even though if we'll see that with the ultrasonic energy at the different supersaturation level, if we'll see on the induction time, then also we can see this that at low energy with the utility of only ultrasonic energy in this much of joule, okay, this much of joule, we can able to we can able to reduce down the induction time of particular zone. Okay. However, at supersaturation of 1.48, okay, we'll have small difference in all of these peaks. Okay, if you can increase the supersaturation level drastically, no time is means at the instant time you can able to generate the nuclei. Correct. However, if low supersaturation would be there, then slight variation in the time that you will see in case of by changing the supersaturation also. So we can control, we can finally conclude out of this that with the application of this ultrasound energy in the crystallization process, both of this induction time as well as metastable zone width can be tailored. And if we can control this to have a control on the nucleation rate as well as the crystal growth in all crystallization experiment. And therefore, we want to use this ultrasound in a crystallization process. Okay. If we'll use this ultrasound in particular one of the crystallization type of anti-solvent crystallization, when the solute solubility is decreased by adding the second solvent, which is known as anti-solvent. Okay, so it's anti-solvent crystallization. If the ultrasonic waves are used at the laboratory scale, what happens in such processes that the rapid and uniform nuclei throughout the sonicated volume, which will lead to smaller and uniform size crystal particles. Also, the agglomeration of the particles are being reduced, and there is a better control over the number of nuclei that are created in the supersaturation zone. And when this is use of ultrasound is obviously when it passes through the liquid, it creates a cavitation phenomena. Then the solvent and anti-solvent occurs very rapidly, and there which will able to get uniform nuclei concentration in a solution. Okay, and also since it is very rapid process, we'll have rapid growth of the particles. So in a small period of the time itself, we'll able to get the particles generated with the help of ultrasound. Okay, so also when the size which is being obtained from the ultrasound assisted crystallization Then size can be controlled with the help of ultrasonic parameters now, because now everything has to be controlled by the ultrasonic parameters, correct? Because induction time and the metastable is being controlled with the help of ultrasonic parameters. Then what are the ultrasonic parameters that you can able to control? So one of the parameter that you can tailor by the ultrasonic is the power intensity, or you can control the ultrasound addition time, and also the time of ultrasound, means time at what time a particular sonication is applied. Okay, so these are the three different ways by which you can apply the ultrasound in a crystallization process, and thereby it will have control on the nuclei concentration, or it will have the control on the uniform supersaturation creation, and thereby the nuclei. Okay, so ultimately you will have control on the crystal size and its distribution. Okay, so we need to just have a control on the ultrasonic parameters. So if I need to do this, then how do I control this ultrasonic parameters, correct? So there are three ways by which you can apply the ultrasound in a solution. Like, you can give the initial sonication only, means you can give the ultrasonic energy till the nucleation is created, then stop it, then let the the mixing is done to create a particular crystals, or for the growth of a particular crystals. So you can give an initial sonication, or else you can continue to give ultrasonic energy till the all the concentration is utilized to uh, for the growth of the crystals, and finally we'll get the precipitated crystals. Or there is a third way by which also you can apply the ultrasonic energy, like you can give in a segment, or you can say interval of times. Give means 30-second time of provide 30-second type of ultrasonic energy, then keep off the ultrasonic energy by 30 seconds, and then in another seconds again you start providing ultrasonic energy. So you can give in interval of the times also this ultrasonic energy, which is known as a pulse sonication. So these are the ways of applications of the ultrasounds in a solution, and we can tailor the process, correct? So everything, the fundamentals that are required to understand the ultrasonic energy, I think so this would be enough for that. Okay, but how a particular assembly is look like for the application of ultrasound? Basically these sounds are applied through the probe, or there are the baths. Okay, so two mechanisms are available with us: the ultrasonic bath and ultrasonic horn. And the bath you can see in the picture. Okay, there is a specific volume, and over that the bottom plate, the transducers, piezoelectric transducers are attached, and they are creating the sound waves by converting electrical energy into the sound energy, and sound energy is then passed through the liquid which is filled in this cavity, in which the beaker can be kept, and the that beaker a particular solution can be kept. So by this is one way of providing sound energy, or through the probes, from probes also, from the tips of the probes you can provide the ultrasonic energy. So two mechanisms are there that can be used for this as per our applications. Okay, and but the thing is, the probe has some limitation, that these probe are having a fixed frequency ultrasound probes, whereas there are some mechanism available for and above that you can change the frequency also in this case. Okay. So so let us say take some of the case studies that are used. Uh, that are giving us, that will give a better idea of the crystallization process. So particularly here, as I said, my topic is the recovery of valuable components. So I'll try to correlate this case studies with the title one. Okay, so I'll take one of the case study of the lactose recovery. Okay, so I'll take one of the small scale dairy industry, which generally makes the paneer, correct? So when they make some paneer, the water that is remaining, if they will throw it out to the environment, okay, that water creates a lot of environmental problems because it has high BOD and COD loading in that wastewater. Okay, you can see here the 30,000 to 50,000 milligram per liter BOD is there in this dairy wastewater. Okay. Then we tried to find it out what is the cause of the enhancement in the BOD, why the BOD is so high in such kind of the wastewater. Then we found that the main cause of the BOD in the dairy wastewater is the content of the lactose. Okay, that the lactose concentration available in that wastewater is, increases the BOD and COD level. Okay. Generally, this is, after you make the paneer whey and throw it out, whatever the water remains, that water remains in contains with the protein, fat, and this lactose contents. Overall, it is known as a whey. Okay. So I'll give this rather than saying the wastewater, I'll say now it's a whey. Okay. But that is considered as a waste. Correct. So what should be done by knowing the chemical engineers that if I need to reduce this BOD or the COD level of this dairy wastewater, what should I do then? Okay, since I know that the lactose is the main content who is responsible to create this thing, then I'll target to recover this lactose itself. Correct. So how to then remove this or recover lactose from the wastewater? Then there are the various processes available for that. You can go for the separations by the membrane separation process also. Okay. You will have another process also through which also this lactose can be removed. But here we have used here the crystallization process. Okay. Particularly, I'll target your crystallization process. It's a very easy process and very economical also. Okay. And therefore, I'll try to recover this lactose available in the wastewater with the help of the crystallization first, and then by using the ultrasound, because it benefits the crystallization process. Correct. And also said, more than 80% of the cause is the presence of the lactose. Okay. So I have here the two choices that, I can recover the lactose also, and recovered lactose can be used as a substrate for the formulation of the drugs also. With that drugs formulation, you can use lactose as substrate, correct? So for making the tablets. So for the better process can become economical and the product becomes valuable in this case. One hand, you are reducing the BOD level. At the other hand, you can able to use it for the tablet making formulation. Correct. So with this problems, okay, we had used here anti-solvent crystallization. Okay. So what happens in the anti-solvent crystallization is that you take the lactose, means lactose. So here it is synthetically, let us say synthetically, we made the lactose solution. We dissolve the lactose in a water and in which the solution is created, correct? And then we added here the different solvent. So we need to reduce the solid solubility in the solvent. So we have added the acetone in that. Okay. So overall phenomena is then becomes on the mixing of this water and the acetone. Well, the uniform of the mixing would be there. Well, uniform of the nuclei of the lactose would be created, and the growth of the crystal will occur. And in form of the crystal, we can then separate and that lactose, okay, lactose crystals from liquid, and we can have a product. So we tried here in the presence of without the ultrasound and in the presence of the ultrasound. Okay. So you can see here the lactose recovery from that lactose solution. In without the presence of ultrasound, we have around 30 minutes to get 70% of the lactose. Okay. When we sonicated or stirred at a 500 RPM. But when we apply the ultrasound in that particular anti-solvent crystallization, or you can say that for mixing the solvent and anti-solvent, you can see the drastic increase in the lactose recovery that is observable within of this 6 minutes. We can have around 82% of the lactose recovery. So by changing this, clubbing this, the anti-solvent crystallization with the help of ultrasound, we can able to recover this component, okay, around 85.26, okay, in this minutes of time. Whereas without sonication, in the same time, we could able to get half only the recovery of the crystal. That means this proves that the application of ultrasound in anti-solvent is useful, and it enhances the lactose recovery. And when we did it in on the, the real wastewater, okay, real way, which is available from the small dairy, industry, we recover this lactose, okay. This is without the applying without the ultrasound. You can say the lactose are being created, but the crystals are in agglomerated form, okay. This is a S11, means this is lactose commercially available. We took some sample and we do the scanning image electronics. Okay. But as soon as we apply the ultrasound in this anti-solvent crystallization process, the agglomeration level, which is observed in case of S12, or without the presence of ultrasound, is being eliminated in this case, as well as most of the particles are uniform in size. Okay. However, completely agglomeration is not, still being avoided. Okay. But the uniform crystal size is seems to be obtained over here in this case. Okay. And the shape also we can able to tailor. Most of the rod-like shape of the crystals are generated in this case, whereas here there is uneven size of tomahawk shape crystal that are obtained. Okay. Which is being, proven by the crystal size distribution diagram also. Okay. This is uniform crystal size distribution. Okay. And this is just in pure limits. We purchased the lactose sample and their distribution was taken, and you can see there is an uneven size crystal distribution is available. So if we can, produce lactose with the help of this technology, we can able to get more uniform crystal size distribution for crystal products. Then we have thought of, another process for the recovery of lactose, but using some cooling crystallization techniques. And here what we did is we have passed the solution of the lactose through some 2 meter of length of channel having the 2 mm of diameter. And the whole of the channel is in two form. One is serpentine form. We made the serpentine form, and another is in coil form. Okay, so we made it through which the solution is passed, and overall assembly is being kept in ultrasound bath. Okay, so the temperature control is done in the ultrasonic bath, and use of ultrasound bath having the facility to supply the ultrasonic energy also. Okay, so we tried it. Okay, and we say that the recovery of lactose through millichannel in the presence of the ultrasound in a cooling crystallization. Okay, so this is the overall study that we did it. Okay, you can see here we required some magnetic stirrer is required. Okay, some peristatic pumps required. We required some for the cooling purpose. Chillers are required. And then in this ultrasonic bath, we had a different coil shape and in a serpentine shape, particular milli channel which is being kept. And the bath having the facility of changing the ultrasonic energy as well as the frequency also. Okay, so we applied that the frequency and the amplitude, and we see the effect of it on the yield of the crystal. You can say the recovery of the crystals. Okay, with the variation of the amplitude, obviously, I mean, both the coil, the recovery is increased. By changing the frequency also, with increasing the frequency, the yield is getting increased. Okay, so if comparing all this together on a one graph, if I'll compare with the conventional cooling crystallization, then without ultrasound, if I'll pass it through that solution in a millichannel, okay, and then if the millichannel, if the 40% of the amplitude at 25 kilohertz is applied, then what is happening? And in the same millichannel with the application of ultrasound with the 35 kilohertz of frequency and 100% amplitude, what happens? So we compared all these methods together, and finally we seen that, you know, yield. Okay, and comparatively in this use of ultrasound also, with increase in the frequency and the power, that increases the recovery of the yield also. So by, you know, changing of this concept also in a cooling crystallization, without the ultrasound, you can see the recovery is very less, 10%. But when that millichannel is clubbed with the ultrasound, recovery is, you know, is 7 times more, correct? Around 7 times more it is, correct? And from the cooling, conventional cooling crystallization, however, it is giving more than the millichannel. Okay, but in comparatively of the clubbing of the ultrasound, again we can have, you know, 10% of increment in the yield. Okay, so this is how, you know, we tailor the cooling crystallized process also for the recovery of the lactose. And we can have a confirm through the size distribution also, that the size distribution in comparison the raw or conventional lactose obtained through the conventional crystallization distribution. You can see this is a pink distribution. This is obtained through the conventional cooling crystallization. Raw means this is just a purchase, marketed purchased crystal we have plotted again over here. And through this ultrasound club with the millichannel, this is the size distribution that we are getting. More of the uniform size distribution that we are getting. So advantage over here that is in comparison the uneven size distribution of lactose in all of the conventional cases can be made as a uniform crystal size distribution, as well as the recovery of the lactose can also be enhanced. However, in this case, you know, applying ultrasound is not changing here the shape of the crystals. More or less, you are having the shape of the crystal in a tombat shape itself. But if you can look at the surfaces in the presence of the ultrasound, that becomes very smooth in all of the 35 kilohertz or at the optimum condition also. Okay, so we can have a control over the crystal size distribution in presence of the ultrasound if that is being done in the millichannel. Okay, so this is one of the other application than the previous application, correct? This is not an anti-solvent. This is a cooling crystallization. Okay, and previous one is the anti-solvent crystallization. Then we thought of why not to use anti-solvent crystallization by reducing the diameter of channel. So we thought of to having the anti-solvent precipitation through micro channel. Okay, so we had, you know, another process which is known as in which we kept a particular, the diameter is less than of 1000 micrometer. Okay, so it comes under microfluidic, correct? So it's a microfluidic anti-solvent crystallization of the lactose, and their process parameter again it is you know, done on the lactose recovery itself. Okay, So here we had a particularly micro channel that are formed over here. You can see this is a micro channel. Okay. So in microfluidic particular, it is divided into part, correct? The primary mixing zone and the secondary mixing zone. So primary mixing zone in which we use the T shape for mixing the initial solution and anti-solvent. So we have a two syringe pump over here in which one syringe we kept anti-solvent and another is filled with the solution, and both are mixed in a T-shaped curve, and then they are passing through this diameter less than 1,000 micrometer and passing through this secondary channels, and then the precipitated lactose we can obtain over here. Okay, so this studies was carried out to know how much enhancement into the lactose recovery can be done. Okay, so when you are going for the microfluidics, then it becomes very uh, very much control is required over here, because the process needs entire the fluid that becomes passing through this entire tube is in laminar region. So the concept here, it is very different than the previous one when it is an anti-solvent itself. Okay, in there the mixing is happened generally by the mixing of the molecules by agitation itself, or the use of ultrasound itself. Okay, but here the mixing is not done because it's a laminar region, correct? So both of the anti-solvent is going in its layer, and the aqueous solution is also passing through this channel through in its layer. Okay, so more the mixing here is occurring just because the diffusion of the solute from the solution to the anti-solvent. Okay, and by altering this secondary zone, by altering this, we are just altering the layers of particular fluids, and thereby we are increasing the diffusivity of the solute between this two. Okay, and by this way, we had, again received a very good size or the crystals of the lactose by this process also. Okay, so these are the different of parameters. Means with the increase of the lactose concentration, we have changed the solvent to anti-solvent flow rate, because we can change that, correct? We have changed the solvent to anti-solvent ratio, and we have changed the temperature also. Okay, so by doing this, like increasing lactose concentration or changing the solvent to anti-solvent flow rate, okay, have affect little change in the percentage yield that we observed. Okay, like in case of temperature changing also, we have seen the effect of that. It has effect on the lactose recovery. Okay, it is obvious that because of the solubility at the lower temperature, we'll get the highest yield in comparison to other two temperatures. Okay, and there are some limits, by which up to you can apply increase the solution. Otherwise, there would be a clogging effect also, that the particular crystal can clog within that micro channel, and then it will be having no use. Then we need to make the surety of that also. Okay, so by doing varying all of this parameter also, the maximum yield that now we have obtained is by 94%. So previously, when it is there in case of anti-solvent with the help of ultrasound, we have reached up to 85%. But if you are changing the process, we can able to increase by approximately 10% of the lactose recovery in this case. Okay. So these are the fundamentals that can be applied, means done to represent this microfluidic precipitation system. Microfluidic is giving the better yield, but however, the productivity is very less. Okay, which is again been proven. Okay, we have seen when the crystal lactose that is obtained. Okay, the different parameters. So we have seen that its size distribution. Okay, and it is the previous one, row lactose crystal size distribution is this one, and we had here the crystal size that was obtained in this case. Okay, is uneven size distribution. So it's not always the case that we'll get the uniform crystal size. By this process, we can able to recover the lactose. We have increased the lactose yield by 10%, but the size control is not done in this case, because here it's very difficult to have a control on the diffusivity of the solute, which is a solute over the layers, correct? So we'll have, uneven side distribution that we are obtaining in this case. So there are the drawback, but the morphology, if we can target over here, then the morphology is very smooth. We have a very smooth crystals that were obtained. Okay. In case of this crystallized particle, you can see here. Okay, this is one image. Okay, very smooth particle that are obtained, but the size is still uneven. Okay, in comparison to the size of whatever the crystal that is available in a market. So this is what about the few technologies, okay, that can be used along with the crystallization process. But since we have, seen that the overall crystallization process is based on the supersaturation level itself, correct? Means saturated concentration has to be brought into the supersaturation level, and at that level, nucleation is happen, and the crystal growth is occurs. That means there are the various other technology that have that can be used to create the supersaturation zone. Okay, only thing you need to remove the solvents. Okay, now this technology would be a different than the previous three technologies, like an anti-solvent crystallization, then the cooling crystallization. Okay, now I'll try to club this membrane along with the crystallization process. Okay, so mostly there are various types of membrane. I will not describe it. Okay, means non-equilibrium based membranes available, equilibrium based available, and we know about that. We have the water purification system is already been available with us. Means at our home it would be there. So that is purely based on the removal of minerals, correct? So basically, we have thought of to use the membrane technology by considering that the opposite of that water purification system. Why not to have the crystals are the product? Means whatever that removed minerals are there should be our solute, correct? And solvent should be removed. Solvent is not used over here. Okay, so in case of evaporation, what happens? The solvent is getting removed by supplying the heat energy, and therefore we are able to, after evaporation, we can able to increase the solution in a supersaturation zone. So same takes the same process, but now we don't want to utilize the heat. Rather, we want to use the membrane, okay, to remove the water. Okay, so if we can remove the water, the solution becomes supersaturation. So that was the concept, to use the membrane to concentrate the particular lactose solution in a supersaturation zone. So we had some, particular membrane setup that we used is the technology that we use, the membrane distillation technology. Okay, so in membrane distillation technology, what happens is, so we can use particularly hydrophobic membrane. And so in at one side, if you pass the water vapor will pass through this membrane, and it permeates through this membrane, and it will then cool by the cooling medium. Okay, so the solution should be kept at the hotter side in this case, and then it will be evaporated. Okay, and then the vapor will pass through the membrane. And since now the steam which becomes hydrophobic in nature, which will permeate through this, and it will go in along with the cooling water. Okay, so from here the water vapor is continuously being removed, so the concentration of solute in this hotter side would get increased. Okay, and this is what we required, correct? This is what we required to increase the to create the supersaturation or make the concentration higher than the saturated concentration. Okay, so we had used the PTFE membrane, hydrophobic membrane, and we had seen on the change, its effect on the change of the flux as well as the concentration increment. Okay. So over the period of time, we can see the permeation. Okay. Permeation is decreases and thereafter it becomes more or less constant. Okay. But initial 2 hours, 1 or 2 hours, you will see the higher flux. Okay. At the same time, with time, if you can look at to the increase or the lactose concentration, okay, if you can observe that with respect to the time, since the flux is decreases, then the lactose concentration will increase with the same time, correct? So more of the water is removal is happens, more of the concentration of the lactose solution would be there, and this is what we require for the crystallization process in the small time. If we can have a higher concentration which can be kept immediately, means based on the metastable John Wade, if you can change the delta T, the crystal can be recovered. Okay, so this is one of the way by which we can able to create the supersaturation zone by clubbing this. Okay, and with this, we had tried to recover the crystal also with the different of the fluxes. Okay, from 1, 2, 3, and 4, 5. All these fluxes we had taken on y-axis, and the recovery of the lactose we observed on the x-axis. Okay, and with respect to the temperature also at the different temperature, correct, 35, 40, and 45 degrees centigrade, evaporative, not membrane distillation, crystallization is obtained. Okay, so at the highest temperature, obviously the percentage level is less and the flux would be more. Okay, the flux is being decreases with decrease in the temperature. Okay, but at the same times, if we can change the temperature, we have the higher level of the yield of the crystal that are being recovered. Okay, so we can have the recovery of the lactose even at the higher temperature. Okay, we have the 40, we can able to recover at 45 degrees centigrade or 40 degrees centigrade, and also 35 degrees centigrade also. Okay, with the help of this technology. Okay, currently we are working on that. Okay, so this is just about to publish, the way we haven't published this. So just I'm discussing this with you. Okay, so to give you just an idea. Okay, so in overall summary of this would be like with the use of ultrasound along with the anti-solvent crystallization, we can have the recovery of the lactose around 83%. Okay, in comparison to the non-sonicated, means without the use of ultrasound samples, that is around 38.96% only. Okay, so we can say that the use of ultrasound in a crystallization uh, is becomes prominent there, and it uh, enhances the crystal growth also, and makes the uniform nuclei size, and creates a uniform nuclei concentration, and creates the uniform supersaturations. Okay, and thereby we are getting the uniform crystal size distribution at the end, and all of this is being achieved by the phenomena like the cavitation events that are occurs, means creation of the bubbles to the collapse. Enormous energy is being generated that are responsible to create the micro streaming and acoustic streaming. All these are responsible to make the uniform supersaturation and maintaining the crystal size distribution. Okay, we have we have seen that by changing the processes also, we can able to change the recovery, like then we use that microchannel for the crystallization of the lactose, and through microchannel, if the lactose is precipitated out, the yield was found to be 94.58%. Okay, so though we could able to increase the yield from around 85 to 94%, but the particle size distribution in this process is a problem which needs to be explored. Okay, then we have discussed about the clubbing of the membrane processes with the crystallization to eliminate the evaporative crystallization. Okay, and we see that direct distillation membrane crystallization process is a possible technique that can be used for the recovery of lactose, particularly by removing the water from an aqueous solution. Okay, the main objective is to remove the water from that. Okay, so these are the summary that we have. We can do with this. Okay, and about the lactose recovery, these are the different processes. Okay, but I'll give you another idea also for the getting some products with the help of another crystallization process, which is known as reactive crystallization. Okay, so Chandrapal, should I go for 5 minutes more?
Yeah, sir.
Okay, okay. So I need to, give you an idea about the another reactive crystallization process also. That is also a very good process and yet to be explored in a crystallization process known as a reactive crystallization process. Okay. The objective of this is also similar, like, you need to reduce the solute solubility in a solvent by a different mechanisms. Here we have a reaction plus the solute solubility is reduced. Like two reactants are here, sodium sulfate and sodium chloride are being mixed together. Okay, in a water. Okay, so they are reacting to each other. They are producing the strontium sulfate, and this strontium sulfate uh, is then become insoluble in the reaction media. So the product solubility, okay, is being decreases. However, reactant solubility is there. Okay, so just my making this changing the solubility of this product through the reaction mechanism is known as reactive precipitation. Means you will get the product simultaneously with the reactions because the product's solubility is reducing in the reaction media. Okay, so reaction media consists all this water as well as sodium chloride, sodium sulfate, sodium chloride. So overall in this mixer, the product solubility is getting reduced and the supersaturation is being created, and strontium sulfate then comes out as a solid form. Okay, and in this reaction also the ultrasound can easily control such kind of the reactions. So we need to just compare this. Okay, so we had taken this reaction, okay, and we did it, and we changed the concentrations of the reactants and some additives we added, and we can able to tailor the amplitude of ultrasound also. We had changed the temperature, and all of this, concentration, temperature change or amplitude, all are having the effect on the induction time. Okay, so most of this temperature is also decreasing induction time, concentration also decreasing induction time. Okay, effect of amplitude is also decreasing the induction time, but induction time is then increase in the presence of the additives. So additives uh, concentration also to be optimized in such cases if it is to be used. Okay, so if you can see here the plot between the uh, with and without ultrasound over the diffusivity of process. Okay, with the variation in the ultrasonic energy. You can see the plot. This is a blue line. Okay, is generally the experimental values, and this is a simulated value. So we have simulated this diffusivity equation at the different ultrasonic energy, and we seen that up to 30% of the amplitude more or less we are getting the diffusivity. Okay, or we can say the break-even point of the diffusivity at the 30 amplitude, and thereafter if you can provide more energy, the diffusivity becomes faster comparatively to the experimental value. Okay, or you can say little deviation that you will observe over here. Okay, so diffusivity, you can see its effect on then yield also. that with and without ultrasound of you can see the blue dot lines are without ultrasound strontium sulfate, and this orange are with the presence of ultrasound. We can see the drastic change in the yield of the strontium sulfate also, and it has the effect on the crystal size distribution. Okay, we without the ultrasound crystal size distribution, and this is with ultrasound crystal size distribution. However, in both of the case, we are getting uniform size distribution, but the distribution is more narrower. Okay, in case of the 50% of in presence of the ultrasound, so we can change the distribution pattern also with the application of the ultrasound. Okay, and if you can see, the enhancement is in the diffusivity in the reactive crystallization is almost 3 times than the conventional one. Okay, this is 3 times the conventional. Our the diffusivity is 1.6 meters square per second square to becomes 4.8 meters square per second square in case of with and without ultrasound. So in a case orally, I can say it's proven that the use of ultrasound technology in a different crystallization process, you can club and you can learn it as per your application. Okay, so I can conclude in 4 sentences itself, 4 to 5 sentences. Like, sonocrystallization has become a prominent method to prepare organic crystals with a desired crystal size and size distribution. And ultrasound means of reducing induction time and metastable zone width, and is dramatically increasing the nucleation rate in crystallization experiments. Tuning the crystallization parameters can be used to tune the crystals that are of particular interest to the industry. Integrating the ultrasound with micro to milli channel would help industry to enhance the recovery of valuable components. The use of membrane technology will help the crystallization process to achieve the desired supersaturation level. And finally, it can be concluded that the advantage of using ultrasound and membrane in a crystallization are indisputable, and therefore its role or their role, I can say, in the crystallization process will grow as the parameter involved in the overall process are better controlled. So this is and flexibility that crystallization process is giving to you because it has a control over the parameters, and controlling the parameters, it will have a better control on induction time and metastable zone width, and thereby the supersaturation level. And overall, we can able to control the final product's property. So with this, I'll end my presentation over here. Okay, this is my research group that is working on the different of ultrasound processes clubbing with the crystallization. Mostly I'm exploring the pharmaceutical application, but here I have tried to give you an idea about some recovery of lactose, which can be suitable as a, considered as a food technology. Okay. And ultrasound can also be clubbed with the another food technologies. Okay. Or wherever you require some modification by changing the driving force, obviously ultrasound will help to change the driving forces as per your requirement. Thank you.
Thank you very much, sir, for giving informative, knowledgeable session to our participants. Sir has covered very nicely the use of ultrasound in crystallization and how to work cavitation phenomena in ultrasound. And another thing is discuss ultrasonic bath and its props, anti-solvents, sonocrystallization of the lactose, and also discuss about application of the ultrasound in cooling crystallization through millichannel. I hope all participants will be explore knowledge in their research work as well as in future work. Thank you. Thank you very much, sir, for giving us your valuable time.
Thank you, sir.